Welcome to Ask and Learn.
In this problem, we have a cylinder which is initially filled with helium gas at a specified state. The helium is compressed polytropically to a specified temperature and pressure, and we wish to calculate the heat transfer during this process. So we assume that helium is an ideal gas, the cylinder is stationary, the thermal energy stored in the cylinder itself is negligible, and the compression or expansion process is quasi-equilibrium. Now, the gas constant of helium is 2.0769 kilopascal meter cubed per kg Kelvin, and the specific heat at constant volume CV is 3.1156 kilojoule per kg Kelvin. Now we get these values from our tables. So the first thing we need to do is calculate the mass of the helium and the exponent N for this polytropic process. So the mass of helium we get from the ideal gas equation, M is equal to P1 V1 over R T1. And since we know these values, we can put them into this equation. So the initial pressure is 100 kilopascals times the initial volume, 0.2 cubic meters, over the gas constant, which we said for helium was 2.0769, and that's kilopascal meter cubed per kg Kelvin, and that's multiplied by the initial temperature of 283 Kelvin. And so we get the mass of helium in this process to be 0.03403 kg. So great, now we have the mass of helium. Now we can use the equation. So we need to find the final volume, so we can use the equation P1 V1 over R T1 is equal to P2 V2 over R T2. And so if we rearrange this equation, we can find the final volume V2 to be T2 P1 over T1 P2 multiplied by initial volume V1. So since again we know these values, we can substitute them in. So our temperatures are 563 Kelvin finally and 283 initially, times the ratio of the initial pressure to the final pressure, which is 100 kilopascals to 700 kilopascals. And that's times the initial volume of 0.2 cubic meters. So we get the final volume of the system to be 0.05684 cubic meters. So now we have the volume of the final state. And the last thing we need to do is calculate N. So to calculate N, we use the relation P2 V2 to the power N is equal to P1 V1 to the power N. So we can rearrange this equation and write it as the ratio of the pressures P2 to P1 is equal to the ratio of the initial to the final volume V1 over V2 all to the power N. And so if we substitute our values in here, we get that 700 over 100 is equal to the initial volume 0.2 over the final volume 0.05684 all to the power N. So from here, if we take logs of both sides, we can find this exponent N for the polytropic process to be 1.547. Now that we have N, we can calculate the boundary work for the system. So the boundary work into the system is minus integral between the two states of P dV. The minus sign is since the boundary work is into the system. And for a polytropic process, that's minus P2 V2 minus P1 V1 over 1 minus N. And this is equal to minus, so we can write PV as MRT. So MR into T2 minus T1. So we just change the numerator. That's over 1 minus N. So now we can substitute our values again. And the mass is minus 0.03403. That's kgs. We suppress the units. The gas constant is 2.0769 in SI units, and the change in temperature is 563 minus 283 in Kelvin. And this is all divided by 1 minus N, which is 1 minus 1.547. And so we get the boundary work into the system to be 36.19 kilojoules. So now we have the boundary work, and that's the energy into the system. So the next thing we will do is write down an energy balance equation if we consider the contents of the cylinder as a closed system. So the energy in minus the energy out of the system must equal to the change of energy of the system, delta E. Now, we want to calculate the heat transfer or the heat into the system, Q in. So the heat transfer plus the boundary work into the system, WB, which we just calculated. So that's WB into the system, hence the sign is positive, must be equal to the change in internal energy of the system, delta U, which is M into U2, little u2 minus little u1, the specific internal energies. So we can write this as the heat transfer is equal to M CV. We replace the internal energies with the change in temperature, T2 minus T1 minus the boundary work into the system. So here we have an expression for the heat transfer. And now we have all these values, so we can substitute them into this equation. So we have a mass of 0.03403. That's the mass of the helium. That's 3403. That's in kgs. The specific heat we said was 3.1156 in SI units, multiplied by a change in temperature of 563 minus 283 Kelvin, minus the boundary work into the system for a compression of minus 36.19, and that was in kilojoules. So all our units are in SI units. We get the heat transfer into the system, Q in, is minus 6.51 kilojoules. So the negative sign here indicates that heat is actually lost from the system.